Okay, now we consider the potential of a uniformly charged disk. So think, for example, of CD, and we have a charge which is uniformly distributed over the surface of this CD, so that we have a uniform surface charge density sigma. Okay, so this is our disk here, and we have a charge Q which is uniformly distributed over that disk, and so we get sigma equals Q over pi r square. R, in this case, is the radius of the disk. So this is the uniform charge density. We want to find the electric potential at a point x along the axis of the disk, at some distance. Now, of course, the symmetry, if you take it here or the other side, it doesn't make any difference. Now, how to proceed? Well, here we utilize our result for the ring. We consider that this disk is composed of concentric rings of charge. So this is one of these rings. So think of rings with different radii, okay, that are covering the whole surface of the disk. And each of these rings has a given radius r, and it has a thickness dr. Okay? So it has, actually it's covering, it has an area, this small area. Okay? Now, this small area of each of these small rings is actually 2 pi r, which is the circumference of the circle, of this circle of radius r, multiplied by the thickness. When this is very small, then multiplied by its thickness. So this gives you the area, the shaded area of each ring in this case. Now, I want the potential of, so what I do, I mean, the strategy is that I find this is my dq. My dq now is the charge that is distributed over each of these rings. And this dq is equal sigma multiplied by dA. dA is the area of each of these rings. And so this dA is this, so it becomes 2 pi sigma r dr. So this is dq. This is the charge carried here. Now this dq will be considered as the charge of the ring. I know the expression for the potential of this ring, which carries a charge dq at this point. I find it. This will be my dv. And then I add up the contribution of all these dq's. In other words, I add up the potential of each of these rings, which have now different radii, so that they cover the whole surface of the disk. And so this is how I find the potential of the whole charge distributed over the ring. So to quantify things, let me say that dV, which is the potential due to dq, which is this, from our result of the ring, is just k dq over, and we know what was the result. It was r square, sorry, in my case, this is small r square plus x square. Okay? It is this. So it is this length here, if you want to call it in this case, for example, r prime. Okay? So the potential from our previous expression was k dq over this r prime, or k dq over r square plus x square under square root. This is the result of the ring. Except now I substitute dq rather than q, because the charge carried by each of these, by this ring, is, I call it dq. Now the algorithm, what I do, this is the potential. I express dq in terms of the charge density and the geometrical dimensions that are given, okay, and then integrate over the whole dV, so to find V. So what's dq here? I just substitute my result. K, it's 2 pi sigma r dr divided by square root of r square plus x square. My V will be the integral of dV. So I integrate this expression. Now it started to be evident from here that you have r dr, so it seems that the integration variable is nothing but r, actually, small r. This is the integration variable. Everything here is constant, including x, here is constant. R is not a constant. X is constant, but r is not a constant in this case, because I'm integrating over r. So this becomes 2 pi k sigma integral. Let me take this inside for a reason that will become clear now. 2r dr over square root of r square plus x square. So my integration variable is r. And how does r vary? R, this variable, which is the radius of each of these rings, varies evidently from 0, when it is at the origin, up to capital R, where capital R is the radius of the ring. So these are the limits of integration in this case. Now, we always check, after you fix your limits of integration, geometrically, you always check the physics that when you integrate this expression over these limits, you are actually including the contribution of all the dq's. And this is exactly what's happening, because when you integrate over dr, you are actually summing up the contribution of all the dq's, which cover the whole ring. And these dq's, the smallest of these rings has a radius 0. The largest will be just at the outer rim of the disk, which has a radius r. So this thing makes sense in this case. And that's a good, physically, it makes, it's sound physically. Now what remains is to carry out this integral. This is a very standard integral, okay? It's just solved by substitution, and the result of integration in this case will be 2 pi k sigma multiplied by square root of r square plus x square between 0 and r. And if you do this, you get V equals 2 pi k sigma square root of r square plus x square minus, when you substitute for the upper limit, this becomes capital R. So this is r square minus square root of, when this is 0, this is a square root of x square, which is just x. So this is the expression. Let me rewrite it here. So V for the ring, the disk at the center, is 2 pi k sigma square root of r square plus x square minus x. So this is the expression for the electric potential of a uniformly charged disk at any point at a distance x along the axis of that ring.